Hi everyone, welcome back. Today we are going to be talking about P3A. It's our first day of talking about radicals. Our objective today is that you will be able to simplify radicals by adding, subtracting, and multiplying, and that you will be able to rationalize the denominator. Now, as we kind of begin today, the first thing we want to discuss is just what a radical expression is. And a radical expression is really just a mathematical expression that has a radical in it. The radical being this symbol right here. Now, normally, we think about that symbol as being called a square root. But it turns out that not all radicals are actually square roots. Some could be, for example, a fourth root, which is why we see that 4 up there in the index spot. The inside of a radical, whatever is contained on the inside, is what we refer to as the radicand. So let's dive into this a little bit more. We first start out with the definition of what we call the principal square root. And what that says is that if A is a non-negative real number, the non-negative number B, such that B squared is equal to A, is denoted by B is equal to the square root of A. And that's what we call the principal square root. Basically, what this is telling us is that if we looked at the square root of 16, for example, we know the square root of 16 is 4. That's because 4 squared is equal to 16. So 4 is the principal square root of 16. Now, let's dive into this a little bit more. So kind of like when we started talking about fractions way back in the day, you probably started out by just simplifying fractions, and then we learned how to add, multiply, divide, subtract those fractions together. We do the same thing with square roots. You should be fairly familiar with this already, so we are going to move through it at a pretty good pace. But anytime you want to simplify a square root, you want to first start by looking at the numbers that are inside. And what I like to tell students to do is just to make a prime factorization tree. And maybe you haven't done one of these in a while, but once you see it, you'll be pleasantly reminded. So a prime factorization tree is just looking at numbers that go into the 160 that we have in the radicand there. So 2 times 80 is equal to 160, so we can break that down. If we did 20 times 4, 20 times 4 is equal to 80, so we can break that down. 4 could then be broken down into 2 and 2. 20 could be broken down into 4 and 5. And 4 could be broken down into 2 and 2. You could have broken down 160 a lot of different ways, but at the end of the day, if you did a prime factorization tree and you broke down each branch, you should see that all of your ending branches, right? This is where our branches end. They just stop. They don't go any further after those points. Would be a 2, a 2, a 2, a 2, a 2, and a 5. What that means for us is that we can actually come over here and rewrite this square root as 2, 2, 2, 2, 2, 5. Now, since this is a square root, one thing we don't tell you often enough is that there really is a 2 that's sitting here in the index. Anytime you see a radical without a number sitting there, it's always assumed to be a square root. But if that was a 3 or a 4 or a 5, we have to handle that a little bit differently every time. Now, what that 2 on the outside tells us is that if I look inside that square root at my prime factorization, right, 2 times 2 times 2 times 2 times 2 times 5, would end up multiplying out to be 160. Anytime I have 2 of the same factors, I can pull out each of those to the front of the radical or to the outside. So since I have 2 2's, I can pull out 1 2. It's called a 2-for-1 special. If I have 2 on the inside, I can pull 1 out on the outside. I have another 2 2's, so this was that first one. And then I had another set of 2 2's, so I'm going to pull out a second one right here. And then we still have the radical and what was left inside. So there was a 2 and a 5. We can multiply those back together to get 10, meaning this simplified would be 4 square roots of 10. Now, this is really just a good exercise here, but there is a really easy way to check this too. If you go back to your calculator and you just type in the square root of 160 and you get the decimal approximation of it, you should get the same answer if you go back and type in our simplified form. We still get that exact same decimal. We haven't changed it, we just made it look differently, and in turn it's going to be easier for us to end up working with. Let's move on to the next one. Let's go to the one right below it here for a second, then we'll jump in. Those have a little bit more multiplying to do. Now, looking at this particular one, we now see that we have variables inside. Again, there is no index that's indicated to us, so we know that that must be a 2 that's sitting there. That's telling us we're looking for pairs of things to pull out. The way we're going to start this is we're going to start by just looking at that 175, and let's break that down. So 175 is 25 and 7. And 25 is just 5 and 5, and 7 can't be broken down anymore. Now, I just want you to think about this for a second. We're going to do the full expanding of this. So if I expand this, since my endings were 5, 5, and 7, I can rewrite this as 5 times 7. X to the fourth, of course, just means x times x times x times x. Y to the third is just y, y, y. And then we just have the 1z. We've just fully expanded that. We've pulled it apart. We've separated it a little bit. But if I were to actually go through and multiply each of these pieces back together, we would find that we haven't changed it at all. It's really the exact same thing still. Now, since our index is 2, we are looking for groups of 2 of the same things to be pulled out. So I'm just circling up things that have 2 of each of them. Now, anytime I have a group of 2, I can pull one of those to the outside, right? 2 for 1 special. So I'm going to be pulling out 4 things total. So first thing I'm going to start is by putting that 5 out front. I know that I'm going to pull out 2 groups of x's, so we're going to turn that into an x squared. And then I'm going to pull out 1 group of y's, so I'm going to have just a y. And then we come back to our radical, so we're still going to be at the square root of whatever's left inside. So we were still left with a 7, we were still left with a y, and we were still left with a z, making this our final answer. Now, again, this is something that's a little bit harder than the last one to check because we have all those variables in there. So we really want to build up those skills and make sure we know how to simplify. Again, this is something we've been doing for a while, so I'm guessing you're pretty familiar with it at this point in time. Let's look at a couple of multiplying ones now. This is where it starts to get a little bit more interesting for us. So when we want to multiply radicals, and I'll explain this in a little bit more depth in a second, I always like to tell my students that it's the outsides times the outsides, and then it's the insides times the insides. And with any radical problem, we always finish by simplifying. Now, if you notice, on the second radical, there is no outside number. So we can put a 1 there to hold that spot if we want. If I multiply 10 times 1, I would get 10. And then since what was left was inside the square root already, we're going to keep it inside the square root. 3 times 15 would give us 45, and then that x will be tacked on right there. Now, we're not officially done with this problem. We still need to go through and simplify if possible. Now, this one in particular is going to look a little different than the last one because we do have a number on the outside over here. So we need to deal strictly with the inside to start, and then that 10 is going to come play a role at the end. So let's first start by looking at the prime factorization of 45. We know that 45 is really just 9 and 5, and 9 can be broken down into 3 and 3, and 5 can't be broken down at all. That means this whole expression could then be rewritten, now I'm going to put the 10 on the outside, as 3 times 3 times 5 times x, right? Because 3 times 3 is 9, 9 times 5 is 45, 45 times x is 45x. We haven't changed anything. And then we just want to do our 2 for 1 special because, again, we don't have an index indicator, so it has to be 2. So we can pull this 3 out. Now, that 3 is going to be multiplied by whatever number's on the outside. 10 times 3 is 30, so we get 30 square roots of 5x. And we're done. So we started out by simplifying. We practiced doing that with variables. And now we are going to kind of start building upon that. This last problem we had to multiply first, and then we simplified after that. Looking at the last problem in this block, Again, we're going to sit there. It wants us to multiply these together. So to multiply, we take whatever our outside numbers are, in this case 1 and 4, multiply those together, we would have 4, and that number is going to stay on our outside. Then we are going to come over and we are going to multiply our insides together. So if I multiply 18 and 3, I should get 54. And then multiplying my a's together, a squared and a to the 5th, I would have 7 a's total. Remember that when I multiply two things with the same base, we add our exponents together. Now we need to just go through and simplify. So to simplify this thing, we again look at the prime factorization. So 54 could, let's just break it up into 2 and 27. And 27 could just be 3 and 9. And 9 would be 3 and 3. And none of those pieces break down any further. 2 is as good as it gets. 3, 3, and 3 are all as good as it gets. That means we can rewrite this thing as 4. Again, we are looking at the square root of 2 times 3 times 3 times 3. And then we have a to the 7th. Now, you could string out those a's if you wanted to have 7 of them and then circle your pairs and pull it out. Or we can just think a little bit more methodically about it. And that's what we'll do in this particular one. So again, we look for our pairs. I can pull out a 3. Remember that 3 gets multiplied to the outside number if there is one. So 3 times 4 gives us 12. And then let's think about the a's for a second. Since I have 7 a's, if you think about it like shoes, if I had 7 individual shoes, how many pairs could I make? And hopefully you could sit there quickly and say, well, if I had 7 shoes, I know a pair takes 2, so I could have 3 pairs total. And maybe another way to think about that again is just to string it out if you like that better until you start to see this pattern. If I had 7 A's, here's 1 pair, here's 2 pairs, here's 3 pairs. So that's why I'm getting a A to the 3rd on the outside. I'm pulling out 3 A's. And we're still going to be left with the square root. And we just can't forget about the 1A that we had left over. So inside, we still had a 2 and a 3. So that gives us 6 when those get multiplied together. And A, making this our final answer. Simplifying is going to be a part of every problem, so we're going to practice it in just about every one that you see. Let's more formally define multiplying radicals here. So when multiplying radicals, multiply each of the coefficients, which are your outsides, and multiply each of your radicands, which are your insides. Down here we have an example for you. As you can see in this problem, the first step, we took 4x and 5x squared and we multiplied those two things together to form our outside number. 4 times 5 is 20, x times x squared ended up giving us 20x to the 3rd. Now, following that, we then took the inside numbers and multiplied those together. You can see that right here, 3 times 2x, and that gave us 6x, and notice how that stayed inside of our square root over there. Right, so it's the same process that we're just going to continue to follow here. So if we look at another example, to do this, we want to first start by multiplying our outside numbers together. When I multiply 2 and 5 together, I know that I'm going to get 10. And then we want to multiply our insides together. So 5x times 8x would give us 40x to the 2nd power. And last but not least, we need to simplify. So to simplify this, 40 is just 4 and 10, 4 is 2 and 2, 10 is 2 and 5. So I could rewrite this as 2, 2, 2, 5, and then x to the 2nd power, or xx if I wanted to. With a 10 on the outside, we're doing square roots again right now. So I can pull out a pair of 2's, and I can pull out an x. So I'm going to be left with 20x on the outside. 2 times 10 is 20. And then on the inside, I'm just going to be left with whatever 2 times 5 is, which was 10. Hopefully this is starting to bring back and shake off those cobwebs in that summer math brain of yours. Here's the next one. If you look on this one, you'll notice there is no outside number in front of either of these two. And that's fine. If there is no outside number, then we just need to multiply the insides together and simplify. 7 times 5, 35. X times x squared is x to the third power. Simplifying this, if I try to simplify 35, I would find out that that's just 5 and 7, right? 5 times 7 is equal to 35. But neither one of those two break down, and there are no pairs. And what that means for us is that 35 is really as simple as it gets. We can't reduce that any further. Now, x to the third is really xxx. So we know there is a pair of x's that I'd be able to pull to the outside. So my final answer would be that x. Then I have 35, but I do still have that x left over. So x square roots of 35x. Let's talk about adding and subtracting radicals here. Now, in order to add or subtract radical expressions, we got to first understand what like and unlike radicals are. Like radicals can be added or subtracted with the same as with like terms. Unlike radicals cannot. Sometimes you will need to first simplify radicals to check and see if they are in fact like. Here's our first example, very basic. This is what we would consider like radicals. Like radicals are radicals that have the same thing on the inside. And sometimes this is easier to just sit there and explain verbally. So if I had 3 square roots of 5 and I added that to 4 square roots of 5, how many square roots of 5 would I have? Well, 3 plus 4 gives us 7, and that is how we get our answer. Looking at radicals that are not alike, we have right here the square root of 12 and the square root of 48. On the surface, we can't add or subtract those at all because they're not like. That's how addition and subtraction with radicals is defined. But we should always be sure to go through and simplify. So if I broke down the square root of 12, which is what this one was, and the square root of 48, I looked at their prime factors. They then went through and said, well, let's pull the 2 out, which is why we see it there. And this one pulled out a 2 and a 2, which got multiplied together to make a 4, which we see over here. And they were both left with a square root of 3 inside. Notice how when we simplified those, these two things ended up being like radicals. So if I had 2 square roots of 3 minus 4 square roots of 3, 2 take away 4 would give us negative 2 square roots of 3. This is very much the same as if we were dealing with just like terms. So if I had 2x's and I took away 4x's, right? Notice how x is just taking the place of each of those two radicals right now. 2 take away 4, I'd say that, well, I have a minus 2x, right? X takes the place of square root of 3 in this problem. Notice how that radical does not change when I am when I'm adding or subtracting radicals. It still stays the square root of 3. We might need to simplify it first, but it stays the same when they get combined. Let's look at another example here. Our directions are to simplify as much as possible. So right here, first thing, we can see that we're adding radicals together. So we want to see if we have like radicals. In fact, we do. So if I come over here and I take 2 plus 1 plus 3, I would get 6. And I have 6 square roots of 3, and we're done. Adding and subtracting is really easy if the radicals are already the same. If they're not the same, we have to do more work to start. Because sometimes they might be able to be combined and other times they can't. So, again, let's look at the prime factorization. 8 is just 2 times 4, and 4 is 2 times 2. So I could rewrite this as 2 square roots of 2, 2, 2. 32 could be broken down into 8 and 4, and 8 is 4 and 2, and 4 is 2 and 2, and 2 and 2. So I could rewrite this as 2, 2, 2, 2, 2. Those are where those 5 2's are coming from. Now we just simplify by pulling out pairs. Remember, 2 for 1 special. Anytime I have 2, I can pull out 1. So in this first one, I'm going to pull out another 2, and then 2 times 2 would give us 4, so I'm going to be left with 4 square roots of 2. And on the second one, I'm going to be able to pull out 2 2's, so I'm going to have a 2, and a 3 on the outside. 2 times 2 times 3 would give us 12. And and I'd still have that square root of 2 on the inside. And those are, of course, being subtracted. Now, if we look at that once we've simplified, we can see, hey, these are like radicals, so we can go a little bit further. 4 take away 12 gives us a negative 8 square roots of 2. And we're done. Looking at another one here, we see some square roots that are actually maybe a little bit nicer to work with. Square root of 16 x to the second minus the square root of 25 x to the third. So let's break these down like we have been. So this would be 4 and 4, 2 and 2, 2 and 2. Remember, anytime I have a pair, I can pull it to the outside. So it looks like we're going to eliminate that number on the inside. So 2 times 2 would give us a 4 on the outside because I pulled out 2 2's. And it looks like, actually, if I pulled out the x as well, do you notice how the radical disappears? There's nothing left in it, so it's gone. So this whole first radical can just be simplified down to be 4x. And that makes sense because 4x squared, or 4x times 4x, would equal 16x squared. Now for the second one, when I break down 25, I would get 5 and 5, and then I would get xxx. So I can pull out the 5 to the front, I can pull out an x to the front, and I would be left with 5x square roots of x. Now, this is in fact as far as this can go because of the fact that we don't have like radicals. This one has a radical that is the square root of x. This one doesn't have a radical at all, which means they can't be put together any further. This is as good as it gets. Last problem, I'm going to leave this one for you as practice on your own. Start by simplifying. See what can be pulled together and what can't be pulled together. There's no guarantees that all of that is going to be able to be put together. Sometimes you might only have, let's just say, 2 of these terms that could actually be put together at the end. And you might have one term that's kind of the odd man out. So your ending expression could very well look like something like this. All right, last 2 problems we have here. We really got to put it all together here because we're asking you to multiply and to sit there and add and subtract and simplify all at the same time. These are the problems that we're really here to work on. So, in order to do this, we can see right here that we have a distribution that needs to happen. That 2 needs to get distributed to both of those 2 terms. Now, that 2 is an outside number. So that 2 can only affect the 3 and the 5 here. It's not going to have any impact on the inside radicands. That's 6 and the 3. So if I take 2 times 3, I would get 6 square roots of 6. If I take 2 times 5, I would get 10, and I would still have the square root of 3. Same thing is still going to happen over here. If I multiply negative 4 to here and negative 4 to there, it can only affect the outside numbers. Looking at this first term here, you might notice how there is no outside number on this. So we can replace it with just a 1 if that's easier for us to think about. So negative 4 times 1 would be a minus 4, and then the square root of 3 still stays and gets tacked on there. And then negative 4 times a negative 2 would be a positive 8, and the square root of 6 will stay there unchanged. From here, we need to sit there and combine like terms. So 6 square roots of 6 plus 8 square roots of 6 would give us 14 square roots of 6. And if I have 10 square roots of 3, take away or plus a negative 4 square roots of 3, same thing, we would be left with 6 square roots of 3. Now the very last part we should check is if these can be simplified. And hopefully you're saying, well, 6 is just 2 and 3, nothing to pull out or fix there, so that's good. And 3 is just 3 and 1, nothing to pull out or fix there. We're good. Neither of these 2 numbers is able to get smaller, which makes this our final answer. Last problem we see, sometimes we call these foiling problems. I'm not a big fan of FOIL. I like the idea of just a double distribution problem. So we are going to distribute this first term to each of these second 2. And then following up on that, we are going to multiply the second term by each of those 2 as well. So we got to be careful here in our multiplications. And maybe to do that easiest, we might actually just write this out. So our first multiplication is going to be 5 square roots of 3 times 1. So I could write that out as 5 square roots of 3 times 1. And then our second multiplication would come from right here. So we would have 5 square roots of 3 times a negative square root of 6. Our third multiplication would be just 4 times 1. And our last multiplication would be 4 times a negative square root of 6. And from then we can just do those multiplications and actually start to simplify. So again, 1 is an outside number, so 1 times 5 would give us 5 square roots of 3 here. Moving on to the next one. There is no other outside. Actually, there's a 1, I guess. So 5 times a negative 1 would give us a minus 5 on the outside. Square root of 3 times the square root of 6 would be the square root of 18. Right, so all of that gives us that. All of that gives us that. 4 times 1 is easy. That's just 4. And our last one would be 4 times a negative square root of 6. Remember, there's a negative 1 here. So 4 times negative 1 would be a negative 4 square root of 6. And again, that 4 doesn't affect the 6 because of the fact that 6 is an inside number and the 4 is an outside number. Now, once we are at this point, we should do our best to simplify radicals if possible. 3 is obviously not going to be able to be broken down. 18 can be broken down into 9 and 2, and 3 and 3, so there is a pair. So let's pull out the 3. 3 times the square root, or negative 5 would be a negative 15. Square root of 2. Slide this all together, make it look a little prettier. Then we are going to have the plus 4. And then we are going to have the minus 4 square roots of 6. Again, 6 is just 2 and 3. So there are no pairs there, so we can't go any further with that. Now, looking at this thing sure looks ugly, and it is. But you can notice that there are no like radicals there, so there's nothing that can be added or subtracted. We've already went through and simplified, which means this is as good as it gets for us, ladies and gentlemen. Lots and lots of review material here with these radicals. I'm hoping this did not all come as something that's brand new to you. If it did, please be sure to reach out to me and we can go over it in more depth. Remember, I'm always here to help if you need anything. Your homework assignment today is going to be worksheet P3A. You're going to only do the evens and problem number 5. I think there's 6 problems total for you to practice. If you're looking at that and saying, hey, I want to practice some more and go a little bit deeper on this, please feel free to do so. Thanks for taking the time to watch. Remember, if you need anything, let me know. Thanks. Have a good day.